Imagine gazing up at the night sky, its stars twinkling like distant beacons while planets and galaxies swirl in the endless tapestry of the cosmos. For centuries, humanity has been enchanted by the prospect of space travel, with rockets serving as our literal and symbolic vessels to the heavens. But what if I told you that rockets aren't our only ticket to the universe? Today, we'll journey beyond the obvious, exploring the cutting-edge science, daring imagination, and real-life experiments that are making it possible, perhaps sooner than you think, to go to space without rockets. To embark on this mesmerizing adventure, let's first define what we mean by going to space. Typically, space is officially recognized beginning at the Kármán line, about 100 kilometers, or 62 miles, above sea level. At this altitude, Earth's atmosphere thins out to the point where the air is too rarefied to support conventional aeronautical flight. Rockets have been our go-to method precisely because they can break free from the stubborn grip of gravity and atmospheric drag. However, the limitations are clear. Rockets are expensive, dangerous, and environmentally taxing. So what other paradigms might one day ferry us to the stars? First, let's travel back a bit in history. While the modern age of space exploration kicked off with rocketry, iconically, the launch of Sputnik in 1957 by the Soviet Union, early visionaries imagined other ways to reach the heavens. In the late 19th and early 20th centuries, scientists and dreamers like Konstantin Tsiolkovsky, Hermann Oberth, and Robert Goddard laid the groundwork for rocketry. But they also toyed with alternatives: giant cannons, high-altitude balloons, and fantastical machines powered by the elements. In Jules Verne's famous novel, From the Earth to the Moon, the journey involves a giant gun. Of course, firing humans from cannons is, let's say, not exactly practical. But these historical attempts weren't wholly misguided. They pointed to the core challenge: how to overcome Earth's gravity in a way that is more gentle, sustainable, and perhaps even routine. Today, science is finally catching up with those dreams. Our fascination with non-rocket spaceflight boils down to three main concepts: using the atmosphere to our advantage, constructing colossal machines, and harnessing entirely new materials and technologies. Let's dive into these possibilities one by one. First, consider an age-old technique, the balloon. It might seem low-tech. After all, balloons have been floating in the sky since the Montgolfier brothers in the 18th century. But high-altitude balloons are having a modern renaissance, making headlines as commercial and scientific payloads flirt with the edge of space. Companies like Worldview and Space Perspective are literally building vehicles that resemble luxury capsules slung beneath behemoth balloons larger than football fields. Here's the science. Massive balloons filled with helium or hydrogen ascend slowly, rising above the troposphere, past the cruising altitude of jets, and into the stratosphere. At altitudes of around 30 to 40 kilometers, roughly 20 to 25 miles, passengers can witness the dark velvet of space and see the curvature of Earth, often in near total silence. While these balloons don't pass the Kármán line, they reach the near space region, enough to deliver awe-inspiring, otherworldly views, and a legitimacy to the experience of turning blue into black. Unlike rockets, these balloons are incredibly gentle rides. There are no roaring engines, blistering G-forces, or clouds of polluting exhaust. Instead, the voyage to the stratosphere is almost zen-like, with a gradual, peaceful ascent. But can we go further with balloons alone? Here we hit a wall. Even with exotic super-pressure balloons and advanced materials, it's difficult to get above about 50 kilometers. Beyond that, the lifting power of even the lightest gases runs out. The air becomes too thin, and balloons lose buoyancy. However, balloons could play a supporting role, lifting cargo or passengers part way before another technology takes over. That brings us to our next imaginative leap, the space elevator. If you've never heard of the space elevator, get ready for a marvel. At once science fiction and serious engineering proposal. Instead of blasting payloads upward, imagine hoisting them skyward, up a tether that stretches from Earth's surface to a point in geostationary orbit, about 36,000 kilometers, over 22,000 miles, above the equator. Here's how it would work. A counterweight extends beyond geostationary altitude, with a cable anchored on Earth and tensioned by centrifugal forces. Along this vast tether, robotic climbers could ascend and descend, carrying humans, satellites, and supplies at a fraction of the energy cost of rockets. The limiting factor is materials science. To build a cable strong enough to withstand not just weight, but extreme tension, you'd need something with breathtaking strength-to-weight ratio, far beyond ordinary steel or Kevlar. Enter carbon nanotubes and graphene. These are forms of carbon atom arrangements with theoretical tensile strengths orders of magnitude above anything we use today. Labs around the planet are racing to make these materials at sufficient scale and cost. Each breakthrough nudges us closer to realizing a launch system that could, in theory, revolutionize access to orbit. Picture it. Instead of a thunderous roar, the first human trip on a space elevator would be almost silent, with views transforming from blue sky to indigo, then velvety black as Earth falls away. The ride, spanning hours or even days, could be as smooth as a train gliding on rails, albeit rails stretching tens of thousands of kilometers straight up. The implications are staggering. Huge satellites, space habitats, components for interplanetary ships, all could be hoisted at vastly lower cost and risk. Prices for payload delivery might drop from tens of thousands of dollars per kilogram to the mere hundreds. Space might become as accessible as another continent. But for now, the space elevator remains in the realm of ambitious proposal, credible and increasingly feasible, but not yet terrestrial reality. So let's look at more near-term developments, blending proven principles with wild new twists. Next, let's talk about electromagnetic launch systems. These approaches use the forces of magnetism and electricity to hurl objects at incredible speeds, dispensing with rockets entirely. The basic physics arises from Maxwell's equations. Send an electric current through coils arranged in a track, and a moving magnetic field results. If you time it just right, the interaction can accelerate a conductor, such as a train, sled, or capsule, rapidly along the track. This principle powers maglev trains, which today glide above their rails in parts of Japan and Europe. What if we scaled up maglev technology? This is the heart of the launch loop and the electromagnetic catapult, sometimes called a railgun or mass driver. Imagine a launch complex built into the side of a remote mountain or running for kilometers along a coast. Objects placed inside special capsules are rapidly accelerated to hypersonic speeds, Mach 5, Mach 10, or more, before flying off into the upper atmosphere, where wings or rocket motors might take over to complete the journey to orbit. A company called Spin Launch is taking this concept boldly forward. Their innovative approach uses a massive spinning arm inside a vacuum chamber to accelerate payloads to speeds near the edge of spaceflight capability. When released, the capsule shoots out at extraordinary velocity, requiring only small rocket adjustments to reach orbit. The kicker: this approach could reduce fuel and emissions by over 70%, radically slashing launch costs and enabling more frequent missions. Electromagnetic catapults have their challenges, namely protecting delicate cargo, especially humans, from the G-forces of acceleration. Still, for launching bulk cargo, such as water, supplies, or even construction materials for space colonies, this method is incredibly compelling. In the long term, hybrid systems could accelerate human-rated capsules at more survivable rates, making electromagnetic launch a key player in humanity's space future. Now, let's entertain another daring idea: skyhooks and orbital tethers. Think of these as hanging bridges in space. Unlike a full-blown space elevator, a skyhook is a rotating or stationary cable attached to a satellite or orbiting spacecraft that periodically dips close to the atmosphere. A vehicle flying up from the ground can rendezvous with the tip of the skyhook, latch on, and be whisked into higher orbit using the cable's kinetic energy. In principle, this could save substantial amounts of rocket fuel, or even eliminate the rocket entirely if clever combinations with aircraft and balloons are used for the first stage. NASA and private engineering groups have run experiments with space tethers, successfully using thin cables to transfer momentum among orbiting satellites. The trick is synchronizing the timing, speed, and attachment. No small feat at orbital velocities. But recent advances in automated docking and precise navigation bring these concepts ever closer to reality. Hybrid skyhook concepts, blending atmospheric aircraft, stratospheric balloons, and space tethers, could one day allow humans to board a space tram, soaring upward with only the quiet hum of electric motors. So far, we've lingered on mechanisms powered by physics and advanced materials. But what about entirely new realms of propulsion? Enter the evolving field of beamed energy propulsion. Imagine a spacecraft with no engines or fuel, just an ultralight sail, similar to the way ancient mariners once plied the seas. On Earth, powerful lasers or microwave arrays track the vehicle, bathing its sail in a focused beam of light. The pressure of photons exerts a gentle yet persistent push, gradually accelerating the craft to astonishing speeds. Small-scale demonstrations, like NASA's Light Sail and Japan's Icaros probe, have already proven that solar sails can harness the sun's energy in open space. Now, scientists are working on ground-based laser arrays that could power ever larger missions from launch to orbit, and possibly to other worlds. Beamed energy propulsion faces obstacles: the need for colossal, precise arrays, and the challenge of atmospheric distortion. But if cracked, the concept could enable launches at a fraction of today's environmental impact, with the only fuel being our abundance of sunlight or electricity from renewable sources. Let's not forget the more speculative but ever-fascinating prospects: anti-gravity drives, zero-point energy, and wormholes. As of today, these are topics for the distant future, or perhaps for science fiction. But they capture our yearning to transcend our current limits. Who knows what the next century's physics will bring? Back in the realm of feasibility, one near-term approach is air-breathing space planes. Unlike rockets, which must carry both fuel and oxidizer, air-breathing engines use atmospheric oxygen, much more efficient for suborbital and orbital insertion. The British Skylon project, for example, is developing a single-stage-to-orbit spaceplane with revolutionary engines that morph from turbojets to rockets at high speed. In theory, these vehicles could take off from a runway, fly into near space, deposit their payload, and glide back. No massive rocket stacks or launch towers needed. Similarly, emerging companies and NASA experimenters are exploring the rocket plane paradigm, where reusable, winged craft accelerate via air-breathing engines and only kick in rocket propulsion at the edge of the atmosphere. This hybrid approach drastically reduces standing costs, uses existing infrastructure, and makes space access as routine as commercial aviation. Now, you may be wondering, what's the closest the average person can get to going to space today without the price tag or risk of a rocket? The answer circles back to high-altitude balloons and parabolic flight. Several companies offer edge-of-space experiences, lofting adventurers in pressurized capsules to the stratosphere, where they can marvel at the world below. Others offer zero-G flights, where aircraft perform steep climbs and dives, giving passengers brief periods of weightlessness, simulating some of the sensations of space travel, if not its altitude. Still, for the true leap forward, we must combine the above innovations, blending materials science, energy breakthroughs, and nimble engineering. Imagine the not-so-distant future. You book a ticket for an orbital excursion, no rocket required. Instead, your journey begins atop a high-tech maglev line, spirits you up a mountain at breakneck speed before transitioning onto a next-generation balloon, climbing quietly through the blue. Once in the upper stratosphere, your capsule rendezvous with an orbital tether, which lifts you, in serene silence, toward a waiting space station. Views out the porthole reveal the clouds thinning, the horizon curving, until suddenly you are weightless, floating in the black, Earth tumbling below in blues and whites. What drives this ingenuity? At its heart, the quest is about lowering barriers, to make space accessible not just to professional astronauts, but to all of us, scientists, artists, dreamers, and explorers. Rockets, for all their power, will always be expensive and energy-intensive. But as new paths to orbit open up, the space frontier will become more like a new world, waiting to be visited, studied, inhabited, and cherished. To sum up, escaping the surly bonds of Earth without rockets is not just the stuff of fantasy. It's a genuine pursuit, rooted in physics and engineering, one that's inspiring legions of researchers, entrepreneurs, and aspiring astronauts. From ultra-high balloons and electromagnetic launches to space elevators, tethers, and beams of light, humanity is reimagining what it means to reach the stars. But perhaps the most crucial element is the willingness to dream, to believe that impossible problems are solvable, that barriers are made to be broken. Every reusable shuttle, every high-altitude flight, every carbon nanotube spun in a laboratory is a step closer to that future. The first time a person flies to orbit without a rocket will represent more than a new technology. It will be a triumph of human imagination, curiosity, and courage. So the next time you look up at the sky, tracing the slow arc of a satellite or the flash of a meteor, remember, rockets blaze the trail, but new paths are already being carved. The journey to space without rockets is no longer a wild dream. It's the next great adventure, and someday soon, when you ask, "How will I get there?" the answer might just surprise you. As humanity stands at the dawn of a new space age, one thing is certain. Our reach will only extend as far as our boldest ideas. And in this pursuit of reaching space, not just by rockets, but by innovation, creativity, and unity, the sky is not the limit. It's only the beginning. Thank you for joining us on this journey through the frontier of science and imagination. If this mission excites you as much as it does us, don't forget to like, share, and subscribe to Space Future Now. Together, let's keep pushing the edge of what's possible and beyond.